A good day to all of you. Today we are going to discuss about the operation of the MOSFET. So before going to the operation of the MOSFET, first of all we have to know about the device structure, how the MOSFET is going to be there. And as well as why we are going for MOSFET compared to BJT. That is also we have to know. Then we will go in detail about the structure of the MOSFET. Okay, so compared to BJT, so what is the difference that we are going to see in the MOSFET is? So compared to BJT, what is the advantages? That is what we have to see here. The first thing is the MOSFETs can be made quite small in size. That means smaller area. So MOSFETs can be made quite small. MOSFETs can be made quite small. That means what? It requires less area on the silicon chip. Okay. So that means compared to BJT, it is going to be occupy a very less area on the silicon chip. That is the first advantage of the MOSFET compared to BJT. And the second one is going to be the manufacturing process is going to be very simple. The manufacturing process is very simple in MOSFETs compared to BJT. Okay, and the third one is the main advantage, it requires less power. So anyhow, whatever the devices we are going to manufacture in today's world, so every device must be take less power. So this one is going to be preferred most, as well as the area. Okay, so these are the major advantages. So one is the major thing, it takes less area, as well as the manufacturing process is simple and it is taking less power compared to BJT. So we are going to prefer MOSFET compared to BJT. And there is a one disadvantage in the BJT that it is a temperature control device. The BJT is going to be what? It is going to be depends upon the temperature. But the MOSFET is not that much affected on the temperature. We can tell that it is not depending upon the temperature, but BJT is going to be depend upon the temperature. So even though there is a change in temperature, automatically its reverse saturation current is going to be changes. It will affects your output current. And already we know that the BJT is going to be a current control device, whereas the MOSFET is going to be a voltage control device. Okay, so these are the major advantages of the MOSFET compared to BJT, and why we are going for the BJT. And one more thing is that due to these advantages of the MOSFET, a more number of MOSFETs, that means I can tell it as 200 million MOSFETs can be packed together on a small area. Okay, so large number of MOSFETs can be fabricated on a single IC chip. Single IC means what? Integrated circuit. Okay, so due to these advantages, what a 200 million MOSFETs can be able to fabricated on a single IC. So we come to know that how much a small size of the MOSFET is going to be there. Okay, and due to these advantages, mostly these 200 million MOSFETs on a single IC can be able to use for implementing in VLSI circuits. Such as the applications in designing a microprocessor and memory circuits. Okay, so these types of circuits can easily able to manufacture by using this MOSFETs, which is going to be occupy less area as well as power, and the manufacturing process also is going to be very simple. So these are the major advantages of the MOSFETs. Now let's see about the generalized MOSFETs. So which MOSFETs is going to be generalized used? So generally used is going to be what? One is enhancement MOSFET. So this enhancement MOSFET is most popularly used. Okay, and we are going to see its operation. We are going to see its device structure first, then we will go for its operation. Okay, so in today's class we are going to see about this device structure of n-channel MOSFET, or I can tell it as n-channel enhancement MOSFET. Okay, so for this n-channel enhancement MOSFET, for simplicity, what I am going to do is I am just removing these things. First of all, I will write the diagram over here. I think I cannot able to write in this same page. Okay, so that I will make this heading aside, and I will write this diagram on a separate slide. Okay, so see here, how this enhancement MOSFET is going to be manufactured is, first of all we are going to see about its construction. So as I told that it's an n-channel enhancement MOSFET. Okay, so for this n-channel enhancement MOSFET, first of all we are going to take a p-type substrate. So the transistor, whatever the transistor we are going to take, the transistor is going to be fabricated on a p-type substrate. I will take this area is going to be very large. Why? Because I have to induce some more materials here. Let it take like this. Okay, fine. So we are going to take what? A p-type substrate first. A p-type substrate we are going to take. Okay, so in this p-type substrate, so this how this p-type substrate will be acts in the MOSFET is, it will acts like a how we are having a basement for a building. So similarly for in the MOSFET we are going to have a basement. To construct the MOSFET we need a basement, so that basement is going to be this p-type substrate. Okay, so in this p-type substrate it is going to be made up of a silicon. Why? Because it is a p-type material, and on this a two heavily doped n plus regions, that is n plus source and n plus drains, are created in this substrate. So I can induce like this. A two heavily doped n plus regions is going to be created, is going to be induced in the p-type substrate in the manufacturing process by VLSI methods. There is a quite scenario, there are some steps for inducing this heavily doped n plus substrate into the p-type substrate. And this plus mark, what is this plus mark indicates is, this plus mark indicates that the material is going to be a heavily doped material, and I am going to call this two heavily doped materials as source and drain. One is source, another one is going to be drain. Okay, so on this we are going to have this source and drain are of what regions which is going to be present on the substrate, and on this top a thin silicon oxide layer, a thin silicon oxide layer is going to be present. So actually this silicon oxide layer will be present from this region to this region, and by using some different methods we are going to remove that silicon oxide layer totally. But as of now I am not including that things and all here. I am directly writing that silicon oxide layer is going to be present between source and drain region. But for this entire substrate, for the top of the entire substrate, the silicon oxide layer will be there. Later, due to some techniques, we are going to remove this entire material, and we are going to keep only in between the source and drain regions like this. Okay. So a thin silicon oxide layer which is having the thickness, I can say it is going to be of typically 2 to 50 nanometers, 2 to 50 square nanometers. This is the thickness of the silicon oxide layer. So it is represented with T0x. So and this material is silicon oxide layer SiO2. Okay, it will act as an insulator. So this SiO2 is a dielectric material which can act as an insulator. Okay, this is a silicon oxide layer is going to be present on the surface of the substrate. This silicon oxide layer, whatever we have drawn, it will covers both source region as well as drain regions. And a metal is going to be deposited on the top of this oxide layer. Okay, I can call it like this only. A metal is going to be deposited on the top of this silicon oxide layer. So this metal, whatever we are deposited, so I am calling this one as a metal. Metal is nothing but a conductor. Okay, so this is a metal which is going to be deposited on the top of the oxide layer to form as what? Why we are depositing this material is to form this material as gate. We are going to give a connection to this metal on the top of the silicon oxide layer, that is called as a gate. So this is source and this one is going to be drain. Okay, so the metal contacts whichever has been given to both source, drain, gate, as well as on one more contact is going to be given here on the bottom of the substrate. So this is the bottom of the substrate. Here also a metal contact is going to be given, and we are going to call this metal contact as substrate or body. We will call it as body of the substrate, and it is represented with the B letter. Okay, so this is the body of the substrate that is going to be present on the bottom of the p-type substrate. Okay, so this p-type substrate itself we will call it as a body. Okay, fine. So at this point what will happen, we are going to have source, gate and drain terminals. We are having source terminal, gate terminal and drain terminal. So and here between source, here source is made up of what type? N type, and a p-type substrate is there. So here a PN junction diode is going to be formed between the source and p-type substrate. One PN junction is going to be formed, and similarly one more PN junction diode is going to be formed between what? Between substrate as well as the drain terminal. So that means what? Two PN junction diodes are connected back to back here. So I can represent in a simple way here how it is going to be present. Okay, so I try to make it easier. So this is a P type and this is N. So like means this is a P and this is substrate. Okay, similarly this is P and this is N. Okay, so that means this is N and this is P. So what is happening here? Two PN junction diodes are there here. So these two PN junction diodes are connected back to each other between source and drain terminals and substrate. Okay, so this is about all the entire device structure. So this is what the device structure of enhancement MOSFET. So and device structure of N channel enhancement MOSFET. Okay, so these two PN junction diodes, whatever it has been present here between substrate and source and substrate and drains, it will prevent the current. It will prevent the current not. It will prevent the current not to flow from drain to source. So from drain to source, no current will flow. Because of what? Because of the presence of these two PN junction diodes, which are connected back to back with each other. Okay, and this MOSFET is also called as insulated gate field effect transistor, IGFET. So MOSFET is also called as what? IGFET, that is going to be insulated gate field effect transistor. So MOSFET means what? First of all, it is MOSFET is going to be the full form as what? Metal oxide semiconductor field effect transistor. Is it right? So metal oxide semiconductor, and FET means field effect transistor. Okay, so as I am having a metal and I am having a silicon oxide layer, and as well as this is entirely what material? Semiconductor, as well as we are calling it as a FET. This is a FET device. So we are going to call combinedly, by using this device structure, we are going to call it as a metal oxide semiconductor field effect transistor. And this gate, whatever the gate it has been present here, this gate is going to be insulated. So insulated at the top of the entire p-type substrate. So therefore we are going to call it as an insulated gate field effect transistor. And due to this gate, whatever the gate it has been present here, so this gate terminal makes the insulation current is going to be in the order of 10 power minus 15 amps. Okay, so due to this gate terminal, whatever it has been present here, so due to this, what will happen? The gate terminal current is going to be very less current, and this gate current is going to be almost 10 power minus 15 amps. It will be there. So almost we can tell it as a zero current. So there will be no current flowing in the gate terminal. Okay, so that is a major thing what we have to know. And one more thing here, and I am going to remove this 2PN junction. Why? Because I have to mention some two things. One is what? The length between the source and drain regions is going to be represented as L, the source and drain regions between this length. Okay, so the area, that is the length of this, is going to be denoted with symbol L, and the width between the source and drain is going to be represented with W. So L and W, length and width between source and drain regions. So this is going to be very important when we are going to know about the operation of the MOSFET. Okay, and finally this range, what is the range of this length between source and drain is going to be 0.1 micrometer to 3 micrometer. And what is the width of this material is going to be 0.2 micrometers to 100 micrometers. So, and we can imagine that as it is micrometers. So as we are telling it as what? Micrometers. So that means what? Almost it is going to be 10 power minus 6, 0.1 into 10 power minus 6 meters. So almost 0.0000, almost we are going to have 6 zeros after the point decimal zeros. So we can think of that how much smaller the area of that MOSFET is going to be there. Okay, so we cannot imagine that size of that particular single MOSFET, the length as well as width. So that's why we can tell that a millions of transistors, millions of MOSFETs can able to fabricate on a single IC. So from this, from this class we come to know that what is the advantage of the MOSFET, as well as how the N-type N-channel enhancement MOSFET, N-channel enhancement MOSFET has been constructed. In the next class we are going to see the operation of the N-channel enhancement MOSFET. We will see in the next class. Thank you. Bye bye.